Welcome. We'll look now at algebra of functions. The idea here is that mathematical relationships defined by functions can be treated almost as algebraic objects. I can add them, subtract them, multiply them, sometimes divide them, and even do something really special with them, where I compose them, which just means having one function applied followed by another one. Most of these things are fairly straightforward and act in the way you would expect. One special case, though, is dividing functions. So the only issue is that dividing by 0 is not well defined. Right? Why not? Well, just to give you sort of an example, let's just look at 1 divided by 0. Let's say that that was equal to x. If this made any sense, I could multiply both sides by 0 to clear the denominator. So this would tell me that 1 was equal to 0 times x, or 1 equals 0, which is a contradiction. So this gives you some idea that dividing by 0 doesn't really make any sense mathematically. It's not well defined, to use a mathematician's language. So when you divide functions, you have to be careful about the bottom. If the bottom is ever equal to 0, you have to exclude that possibility. We'll get into this in a little more detail when we talk about the domain and range of a function. I also want to mention that composition of functions is something that you can't really do with numbers the way you can with functions. So what is composition? What this says is that I have two functions f and g, and I can define a new function based on them. F circle g, which is composition. And what I do is first I apply g, and then I apply f. Similarly, I can define g composed with f as apply f first, then g. So I want to make one remark right off the bat, which is that f composed with g is not the same as g composed with f. And I'll make that example clear on the next slide, but it's very important to keep in mind. So intuitively, one thinks again of this as first applying g, then f. So the picture is I have some input x. First it gets mapped to g of x, and then it gets mapped to f of g of x. So I'm just iterating the application of functions. So let's look at a quick example. The functions f of x equals x plus 1 and g of x equals x squared. I compute f composed with g by first applying g of x, namely x squared, then applying f of x, which is x plus 1, to get x squared plus 1. I can do the same thing to compute g composed with f, where first I apply f to send x to x plus 1, and then apply g to send x plus 1 to x plus 1 squared. And I see that g composed with f is x plus 1 squared, so x squared plus 2x plus 1. So in particular, we see that f composed with g does not equal g composed with f. This is a very important thing to remember. Order matters for composition. It doesn't matter for addition. It doesn't matter for multiplication. It does for subtraction and division. And it does for composition. So we say like subtraction and division, order matters. So sometimes we say this is non-commutative. Commutative operations don't matter for the order. Non-commutative ones do. So let's just look at some examples. I'm going to give two pairs of a pair of functions, and I'll ask to compute the sum of them, the product, and then the composition of the functions. So let's start with addition. So f plus g of x is equal to f of x plus g of x. So 3x plus 3 plus x minus 1, so 4x plus 2. F times g of x is equal to f of x times g of x. So 3x plus 3 times x minus 1, 3x squared minus 3x plus 3x minus 3. So 3x squared minus 3. And then let's look at f composed with g of x. So this is the same as f of g of x. So f of x minus 1, which is 3 times x minus 1 plus 3. So 3x minus 3 plus 3. So just 3x. Pretty straightforward. Let's look at another example. Here I have x squared plus x minus 2, and g of x is e to the x. So for this, I'll have to be a little bit more careful because they're not functions of the same type. One's a second degree polynomial, the other's an exponential function. So let's start with f plus g of x is f of x plus g of x. So x squared plus x minus 2 plus e to the x. Nothing else I can really simplify. F times g of x is f of x times g of x. So x squared plus x minus 2 times e to the x. So if you like, you could distribute this like this. And then lastly, let's look at f composed with g of x. So this is f of g of x. So f of e to the x. So now I'll plug e to the x into the formula for f. So I'll square e to the x, then add e to the x, and subtract 2. So I have e to the x squared plus e to the x minus 2. So now we have to ask ourselves, what is e to the x squared? Well, how does iterated exponentiation work? I multiply the exponents. So this is e to the 2x plus e to the x minus 2. So a little bit more delicate, I think, than the previous example. In fact, we had to use an exponential rule that we saw in Module 1. And this is very indicative of mathematics, especially at this critical level, where you're about to move on to calculus. Things really build. So if your foundation is not firm, if you don't understand basic ideas of exponential functions, polynomials, etc., it can be very difficult to transition forward. But of course, we're doing a great job here. You're doing great. So we're going to continue to build our foundation so you can continue to succeed in mathematics.